Thank you. Thank you for the introduction, and also I'm very glad to be here to share some of our work on projected variational method for high-dimensional Bayesian inference. And yeah, let me get started. So this is a collaborated work with Omar Ganas from UT Austin, and Ifei Wang from University of Stanford, and Wu-Chen Li from University of South Carolina, and also Tom Oliver Rosberry, Ke Wu, and Joshua Chen from UT Austin. Let me give you 3 examples to sort of like elaborate the key component or the elements of the Bayesian inverse problems. So the first example is the inference of Antarctica ice sheet flow. So you can see from here, it's actually a satellite image of the observation of the surface ice flow of velocity in the Antarctica. You can see their red part stands for their large velocity. And well, the ice flow is actually, the ice melting is one of their biggest challenges in the 21st century, I would say, for the climate change. And perhaps if a lot of the bunch of ice get melted, then there's a very high sea level rise. Well, the problem here is we want to infer some of the parameter in the model depending on the data and the model. The model here is a nonlinear viscous incompressible fluid flow, essentially nonlinear and Stokes flow. And what I want to infer is actually the boundary condition. On the right, you can see essentially it's a Robin type of boundary condition, stands for the Bessel and sliding field in the boundary condition. So the parameter itself is a random field, it's a field variable, and it's infinite dimensional. And well, the second example is some recent work on inference for gravitational wave astronomy. As you can see that there are 2 black holes like billions of light years away that spin around each other, and at a certain point, and they merged. So during this process, there is a gravitational wave propagated into the universe. And actually, this has been detected just in recent years. This is one of their biggest sort of like experimental discovery in the last decade for their gravitational wave. So essentially, it's like our Earth is like a ball in the water, and if there's some excitation, some like a wave propagation, you can see that the ball has changed their phase or their position. And then this can be detected by their 2 long arms on Earth. This is the LIGO and Virgo observation of a gravitational wave on Earth. So essentially, as the wave passes by the Earth, there's the shift of the strain, or the light bounce back from the mirror in the 2 long arms. There is a shift of the strain. The magnitude is very small. It's about like a 10 to the minus 22, and it's very precise. On top here, you would see some top here you would see some signal. This is actually a simulated signal. At the bottom here, you would see some like a noise signal. And the model itself is given by the Einstein's field equations for the general relativity. And there are some like codes, for instance, numerical relativity, where you do simulation for the 2 black holes. One postdoc, Melando Fernando, in our group is doing this very aggressive mesh adaptation and wavelet type of approximation for this numerical relativity. It takes a very long time, like at least, for instance, about a week for a full simulation of several, for the full sort of like black hole spin and merge. And well, so there are some key parameters you want to infer. Essentially, the intrinsic parameters of the luminosity distance of the black holes, and also the mass ratio, relative like mass, and also effective spin and magnitude of the black holes. So based on the data that was observed from the LIGO and Virgo observation experiment, and also based on their approximate model, the numerical relativity, and also there are a bunch of other approximate model, some an ODE system, some analytic approximate model. We want to infer these parameters. And then, well, all these models have different fidelity, different computational cost. So I leveraged their multi-fidelity sort of framework and developed some multi-fidelity importance sampling using tempered posterior distribution for this wave inference problem. Well, the next example is about the COVID-19. So this is one of the map in US in September on September 16th, 2020, in about like 18 states, about like at least half of the deaths are linked to nursing homes, and in fact, the total population in nursing homes is only 0.7%, but it takes about like 40% of the deaths in average, and at the early time there is no sort of like a paper articles to study this sort of very striking effect. And we do not take this effect into account because nursing homes or long-term care facilities is sort of like a closed community. And if you do not take this into account, then the parameters you estimate might be not correct. So what we want to do is actually want to infer, the COVID-19 spread and severity parameters. So the data we have collected at that time is here on the left, on top left, we have the number of confirmed cases in one of the states in Texas. On top it is accumulated number of confirmed cases, and the bottom is you have a daily number of confirmed cases, and the number is a very oscillatory, and so we do like a sort of a moving average. The oscillatory is due to their, for instance, misreport or the delay of the report. And not only about that, but also we have data of a number of hospitalized cases, and also number of deceased cases, a total number and daily number. In addition, we have the deceased cases in long-term care facilities, including the nursing homes. So these are the data that we were able to gather. So in order to understand this phenomenon of this large excessive number of deaths in long-term care facilities, we cook up this model. Essentially, it's a SEIR model with additional compartment for the hospitalized cases and deceased cases. But there are two parts. One part is standing for the outside long-term care facility. Another part is the inside long-term care facility. And there is a so-called this contact matrix. For instance, it's due to their family visitors into their nursing homes, or due to some nurses working in their facilities. Well, there are a lot of parameters here in this model. We need to basically learn all of them from the data. And some of the parameters, they're time dependent. For instance, this alpha, alpha stands for sort of like the transmission reduction. So if alpha is a 1, then essentially there is no transmission. You just reduced all the transmission. If alpha equals to 0, then there is no reduction of the transmission. So apparently it is a time dependent parameter because it's depending on their mitigation policy at the lockdown or their humans behavior. So as you can see, these parameters are sort of like a stochastic process. It's also become infinite dimensional parameters that we need to learn. All right, so with this 3 different examples, I'd like to come to this sort of like abstract formulation for the Bayesian inference, where we have a parameter, uncertain parameter theta, and theta is in the parameter field theta, which is in d-dimensional, and d could be finite dimensional, like in the gravitational wave inference, or infinite dimensional, like the random field or stochastic process. And we have observation data y lives in dimension s, and we have a parameter to observable map O here, which might depend on some model. Essentially, it depends on in the last 3 examples of the model output. And we have the observation noise xi, which typically we assume is additive and also Gaussian. And the Bayesian rule states that the posterior is given by likelihood times the prior divided by the model evidence or normalization constant pi y, which is essentially an integral of the likelihood with respect to the prior. And well, the central tasks for the Bayesian inference are to sample from the posterior, as Jacob just talked about, and also compute some statistics, like we want to compute some expectation of the quantity of interest Q with respect to the posterior distribution pi y. And also, as Jacob mentioned here, this model evidence or normalization constant is typically very challenging and to compute. It could be high dimensional, and also the posterior distribution, or essentially here, this likelihood function could be quite complex to compute directly. So, well, in addition to that, there are a lot of like computational challenges, common computational challenges for Bayesian inference. The first is maybe here the posterior has a complex geometry. This is a two-dimensional problem where you have a posterior density, and it's non-Gaussian, it's multimodal, and also it's concentrating a local region. And for this type of posterior, it's typically quite hard to sample from. And the second is parameter lives in high-dimensional space. For instance, in the Antarctica ice sheet flow, after discretization of the random field, you have a very high-dimensional parameter field to infer. And many of the methods suffer from this curse of dimensionality. Essentially, computational complexity would grow exponentially with respect to the dimension of the problem. And then the next one would be the map. The parameter to observable map could be expensive to evaluate. Involves the solving of the larger scale and high-dimensional partial differential equations, for instance. Well, there are also many different computational methods have been developed over the last decade or two to accelerate, to improve the performance of some classic method. For instance, the first one is the accelerated MC method to essentially increase the effective number of samples using Langevin Hamiltonian MC. These dynamics that sort of like use a geometry based on the gradient and hashing information of the likelihood information. And there is this dimension reduction MC, which exploit their intrinsic low dimensionality of their posterior distribution. And there is this randomized and optimized MC, which sort of like solve optimization problem for sampling instead of do the random sampling. And then there is this direct posterior construction of statistical computation. For instance, the first is a Laplace approximation. You simply just construct a Gaussian approximation of the posterior. And there's also deterministic quadrature using sparse Smolyak and high order quasi-Monte Carlo. And then the next is a transport map, which is focused on today. So the transport map were essentially, as Jacob just mentioned, you're going to push the samples from the prior to the posterior, or you're going to push the density of the prior to the posterior density. For the transport maps, what Jacob used was a polynomial, sparse polynomial, for instance. But however, the other representation basis, like radio basis functions or deep neural networks. And then to address their very large scale computation, very heavy computation, people developed various surrogate models. For instance, a polynomial approximation using stochastic spectral approximation, Galerpin approximation, and stochastic collocation method. And there's also model reduction, for instance, a POD, reduced basis method, and also multi-level, multi-fidelity method. So essentially here, what we want to do is actually want to develop some fast and scalable inference method in high dimensions by exploiting the intrinsic low dimensionality in both the parameter and also the state spaces. But today I'm going to focus on the parameter space using projected transport map. And for the state space, well, we have developed this reduced basis approximation in this paper. All right, so let me come to the projected variational inference method. So essentially, it's based on the optimal transport kind of idea. So you want to move a pile of earth or dirt from one location to another location by transport map T here, in a very simple illustration way. To move this pile of dirt to another place, you wanted a minimum cost. So essentially, this is sort of like the optimal transport problem optimization with respect to the computational effort or the energy. And mathematically speaking, in the Bayesian inference framework, what I want to do is want to find an optimal transport map T star from RD to RD. D is the dimension for the parameter. We want to minimize a certain difference between the put-forward map T sharp of pi 0 is prior, to the posterior pi y. And this is measured by the Kullback Leibler divergence, the Kyle divergence. And there are different kinds of representation for the transport map, as I mentioned. Like one of it is polynomial, but here there's another kind of transport map. It's given by a composition of a simpler transport map from T0 up to TL. And this composition map will push all the samples step by step to their posterior. And each of the step is actually obtained from one-step optimization of this Kyle divergence. And this TL, a map of TL for a C to Ln is given by the perturbation of the identity plus this alpha L. And this phi L hat is actually a perturbation map. And that this can be obtained by some gradient descent or Newton method, depending on the different function class you have for the transport map. All right, so there are many different kinds of like the perturbation map. I'm not sure if you can see it clearly, but on the left you have the Langevin MC, where the perturbation map is given by the gradient, the gradient of the log of the posterior with additional random walk, and this is one of the common MC method. And then here, this one, there is no coupling of this samples theta, L, N. So essentially you can run all of them in parallel. There is no like interaction between all these samples. It's essentially a serial sampling technique. And in the middle, you have the Wasserstein gradient descent. The difference is that, well, the first term is the same, the gradient of the log of the posterior, but the second term is different. And on the left, you have the random walk, but on the right, it's essentially the gradient of the log of the empirical density, pi L. So essentially, for instance, I draw a bunch of samples, and then you have an empirical density of this samples represented by pi L. And well, you can approximate this empirical density by different approximation, like for instance, kernel density approximation becomes pi L hat. So essentially, you estimate this density for the empirical density, and then you can compute the gradient of the log of this density, and you can update all the samples. So the interaction of the samples comes from this approximate empirical density, because this empirical density touches all the current samples. Well, on the right, you have the stochastic, Stein variational gradient descent. So it is essentially, the expectation of the gradient of the log posterior weighted by a kernel function, and with additional term of the gradient of the kernel. Now you take the expectation of these quantities with respect to the pi L. Now you do not have to estimate their density pi L, but you only need to compute the expectation, which you can do by sample average approximation. So essentially, as long as you know the samples, then you can compute these terms without a density estimate. So in the continuous level, they're corresponding to, for instance, Langevin MC is given by the overdamped Langevin dynamics, and is the dynamics for the particles or for the samples with the Brownian motion here. And by the Fokker-Planck equation, you know that this corresponding to the density flow. So essentially, the gradient flow of the density pi t stands for the the density of the current samples. And so essentially, this term is given directly by the divergence of the pi t of this gradient. This is a variation of the Carroll divergence with respect to pi t. So it's actually the gradient flow of the density in the Wasserstein metric. And so from the Wasserstein gradient descent, well, due to this approximation of this pi hat, well, you can visualize as a sort of like approximate of the mean field Wasserstein and dynamics given by this term. And by Leibler equation, because it's a deterministic process, you would get the same Wasserstein gradient flow. But for the Stein variational gradient descent, in the continuous times corresponding to the Stein dynamics, where this phi t is actually a projection of this term of this gradient log pi y minus gradient log pi t into this kernel space. It's called reproducing kernel Hilbert space. So the projection into this space gives you a very simple, evaluation of sort of like these different terms, but it does not involve the estimate for the current density pi t, but rather just a simple average approximation would be fine. And then it's corresponding to the Stein gradient flow. In fact, what you can see is here that you have the same structure, except for this phi t is a projection of this term into the reproducing kernel Hilbert space. So essentially, there are some of like the most popular particle-based methods, but these methods they suffer from cursive dimensionality in high dimensions, all of them. One of the illustrations is for a simple linear inverse problem example. So we want to measure the sample goodness by, for instance, a sample variance compared to the reference value. The reference value for the linear problem is given explicitly, and you can compute their error for their sample variance. So computing the mean square error with respect to the increasing dimension of the problem in log scale, we can see that for a Stein variational gradient descent, this variance becomes less and less accurately approximated. So essentially, kind of you can see from this plot that the accuracy for the sample variance approximation is lost. But if you do some a projection or dimension reduction, you can sort of preserve the accuracy. And this is essentially the idea that we want to explore. But however, what is the intuition behind their the projection or the dimension reduction? It comes from that the you pose the problem is typically the data only inform so part of the parameter. It's essentially inform the parameter in a low dimensional subspace. Or in other way, their posterior and the prior, they're only significantly different in a intrinsically low dimensional subspace. For instance, here's a sort of like the subspace in the leading dimensions where you have the blue as a prior marginal density and the red as a posterior density. You can see they're quite different. But however, as you go to higher and higher dimensions, then that becomes essentially the same from the marginal one-dimensional density and also two-dimensional density. So you can detect this is sort of like information of the subspace by some derivative information, either gradient or Hessian information, for instance. It's being used in these papers for MCMC and also sparse grid quadrature. Well, more in detail. So how to compute the basis for the subspace. This is a way to compute it. This is so-called data or likelihood informed subspace. It's given by the eigenvectors of this generalized eigenvalue problem. On the left here, this H stands for the data information. On the right here, you have the C. C stands for the prior covariance information. So this H can be constructed in different ways. And this is one of the ways. It's given by the expectation with respect to the posterior, which is here, and this integrand is the gradient of the log likelihood function, and this is a gradient of log likelihood function transpose in infinite dimensions, for instance. And this is so-called gradient information matrix. And so this includes the data information. And then if you compute this generalized eigenvalue problem, if you solve it, the eigenvalue actually stands for if the eigenvalue is very big, that basically means the data tells you a lot for this dimension corresponding to this eigenvector. And if the eigenvalue becomes very small, that basically means the data doesn't tell you much. It's primarily coming from the prior information. So here's an illustration by the COVID-19 example. In total, we have about 1,488 parameters, and you can see as you push forward by the Stein variational gradient descent, in step 0, you have the decay of the eigenvalues in log scale, the absolute value of the eigenvalue in log scale. The case is like 7 orders of magnitude in the first 50 dimensions out of almost 1,500 dimensions. And as you push the samples step by step to their posterior, you can adaptively construct this subspace, because here it sees expectation with respect to the posterior. However, you cannot draw the samples from the posterior directly. So you can compute this expectation by the current samples. So you can drive all the samples step by step to the posterior. And then along the way, you can adaptively construct this subspace. And this is a decay of the eigenvalues at different, each of the 10 iterations of the algorithm. And you can see still decays significantly. And so essentially, we only need to care about 20 dimensions instead of the for about 1,500 dimensions. And so what we're going to do here, we'll do the projection. We have the basis of the subspace formed by this eigenvectors. Let's say are dimensional, and then we have the complement here. We can project this parameter into the low dimensional subspace. This is a projection, and then we can define a projected posterior, which is given by it's the same term of the prior, but here you have a profile function, which is a sort of like approximation of the likelihood function, and then you have a normalization constant, so we call this projected posterior. And but what kind of profile function can we compute or define, right? And well, here's a sort of like the optimal profile function. Can decompose the prior density into this subspace in dimension R, and also the complement in this way. And here we denote, remember here, previously we have the theta, but here we have the coefficient W. And now, so this is a marginal density on W. It's given by the integral of this prior integrated with respect to the V per in the complement subspace. And then we can define the conditional density here, which is given by the prior divided by the marginal density. Now we can define the profile function pi star, which is an optimal profile function, as an integral of their likelihood function with respect to their marginal or the conditional density. And in practice, you do not compute this high dimensional conditional integral, but rather do some sampling from this complement subspace, because this samples wouldn't be different from the prior too much. And so the optimality in the sense of the projected posterior difference between the projected posterior and the true posterior in the chiral divergence is sort of like is a lower bound for any type of projected posterior defined above. Well, so now we can define the projected, for instance, in the Stein variational gradient descent or the Stein variational Newton algorithm, we can define in the following sense. So first we decompose the parameter into the subspace and complement. And then, here is our sort of like the projected posterior. And we decompose the prior into this subspace and also the complement subspace. This is our profile function. And now, since all the uncertainty that we cared about in this theta R, which can be represented by W, now we can redefine our prior, as a prior for W, and also the posterior for posterior of W. And then this would be a low-dimensional Bayesian inference problem. So we can run the Stein variational gradient descent or Newton method to solve this problem. And where when you compute the gradient adhesion, it's kind of like the projection of the gradient adhesion of this log posterior onto the subspace formed by this psi. So this is sort of like the illustration of how this algorithm works. And here on the left, you have the high dimensions. Each of the dot stands for one dimension, and all the dimensions talk to each other for each of the iteration. And on the left, we have like the algorithm that touches all the dimensions step by step forward. But on the right, you first do the projection from the high dimensions to the low dimension, and you run the algorithm in the low dimensional subspace. And there's also some like tricks to tune the local curvature in the low dimensional subspace depending on the eigenvalues. But anyway, so once you run the algorithm, it becomes sort of like a stable or converged. You're going to prolongate it into the high dimensions. And because remember, we constructed the subspace step by step adaptively. So we run the algorithm in another subspace until a certain convergence. And a projected error for the projected posterior and a true posterior can be upper bounded by this trailing eigenvalues. Suppose that we have the very fast decay of the eigenvalues. This projection error could be very small. We developed this algorithm both in the gradient descent sense and also the stochastic, the Stein variational Newton sense. Okay, so here's an example to show the difference between the SVGD and the PSVGD. So we have a conditional diffusion problem. And now our theta, the parameter, is a stochastic process. It has a prior of Brownian motion. And so we have the solution U as a conditional diffusion here. And we're going to draw a synthetic sample, which is a red, the true sample. And so we're going to solve this problem. Here, this is a synthetic true solution. And we add up the noise, which becomes a noisy data as a black dots. So now we can run the two different algorithms. One is SVGD, another projected version. We can see clearly that while the posterior mean sort of like converges to the true posterior, but however, for the SVGD, it doesn't. And And also their credible interval covered by their sample, like let's say 90% of credible interval covers the true parameter quite well. And on the left, you would see the sample. On the right, you would see their solution and see similar behavior. Yeah, sure. Well, this is the same number of iteration. So yeah, it's not yet converged. But however, the algorithm, is sort of like the computational complexity is proportional to their exponentially bad with respect to the dimension. So essentially, the number of iterations would be super large if you want it. Continue this process for the Stein variational gradient descent. This is sort of like the scalability demonstration. On the top left, it is the decay of the eigenvalues for different parameter dimension coming from different discretization from about like 300 to 16,000. And you see similar behavior of the decay of the eigenvalues. That essentially means the intrinsic dimension doesn't change much as you refine your discretization. And on the right, it is a plot to show the average step norm. So every time you move your sample step by step to the posterior, the step norm or how much you move, it doesn't change much with respect to the parameter dimension. So essentially, this algorithm solve is scalable with respect to the parameter dimension. And also at the same time, it's scalable with respect to the number of particles. So the number of samples from 64 to 512, you can see similar behavior, similar decay of the eigenvalues, and also similar decay of their, sort of like the step norm for their samples. So this is this algorithm can be parallelized because, you can sort of like parallelize all these samples into distribute them into different processors, and you can compute, the expensive part like the likelihood and also their gradient into different processors. So you can parallelize them, and these are different components like computing the gradient, update the kernels, update the samples themselves, and also the total computational cost. You can see with increasing number of processor cores, you get the linear sort of a decrease of the time, total computational time. So essentially, this algorithm is also scalable with respect to the number of CPU processors, let's say. And well, the last one was about projected Stein variational inference. This one is a projected Wasserstein variational inference. The big difference is here. In the Wasserstein gradient descent, we have to estimate this this empirical density by, let's say, kernel density estimate using some kernel functions. But now, if we project into low dimensions, it's a similar, dynamics, but you estimate this kernel density in the low dimensions. And we know that the kernel density estimate has a problem of kernel dimensionality. Once you go to very high dimensions, then the kernel density estimate it becomes exponentially bad. So we can project into this low dimensions and preserve the accuracy of the kernel density estimate. And in fact, it's not only about their their kernel density estimate accuracy, it's also about their convergence of the dynamics. So for the two Wasserstein gradient flow, one is in the full space, another in the subspace. What we can show is that on the suitable assumptions, for instance, if the log likelihood is strongly convex, and there holds this relation. So essentially, the gradient flow of their Wasserstein gradient flow problem, it converges exponentially. But however, this exponential rate, this lambda d, is the smallest eigenvalue of the Hessian of the log likelihood. In high dimensions, this smallest eigenvalue of the Hessian, supposes strongly convex, it will be very small, it's close to zero, so it converges super slow. And if we project into the low dimensions, this becomes lambda r. Lambda r is much bigger than lambda d, which essentially means the gradient flow in the subspace will converge much faster than the full space. This is another illustration for the Stein variational inference behavior.
Field limit, or I mean, the kernel doesn't appear there.
The kernel doesn't appear here. I mean, this is a sort of like abstract. So we suppose that we have infinitely many samples, and we have this is the convergence in the density. It's not the dynamics, it's in the density.
Oh, I see.
Yeah.
Okay, right. So it's a standard estimator, so to speak.
Yeah. Yeah, that's right. And yeah, here's a very simple plot to show the convergence of these different methods. As I here, we have a linear inverse problem. We have a parameter with Gaussian distribution. This is a covariance term. And we have a 15-pointwise observation with 1% observation noise. We use 16 samples. And here's the number of iterations for the different algorithms. And we measure the sample mean and also sample variance compared to the true posterior mean and posterior variance. Here on the left, we can see, in the green and then the magenta, well, it is there are SVGD and WGD, so converges very slowly, and the PSVGD and the PWGD converge much faster. For their sample variance, you can see that PSVGD converge much faster than the others, and so this is essentially sort of like a demonstration of the convergence of the different dynamics. Let me come back to this application that I brought on early on. So here's the data that I sort of like illustrated, and here's a model. And here's the description of the model is essentially a ODE system of 16 components, and there are a lot of parameters of time dependent. Like for instance, as I sort of like introduced a little bit before, this transmission reduction factor alpha is a time dependent. And then to solve this problem, this is a very high dimensional problem, very non-convex because the model is quite involved. What we did is actually, we first define our loss function. The data is put in the logarithmic scale because many of the the cases, confirmed cases, number of disease cases, initially they grow exponentially. We put them in log scale, and also use both accumulated data, the accumulated number of confirmed cases, and also the daily data. Use both data for the stability of the optimization problem. And then the last is, we use different weights for different, data misfit, like the number of hospitalized, number of confirmed cases, number of deceased cases, and also a number of daily cases. We put different weights. These weights are put proportionally to their sort of like a standard deviation of the data. It reflects their variability and reliability of the data. And here's a regularization term of all these different parameters. And on the top, we have 4 different time-dependent parameters. We put both like a smoothness, for instance, we put H1 norm here. Like we don't want to change the parameter too rapidly for the time-dependent parameter. And we also put some like evidence and some reference value, for instance, for the time-independent parameters. We gathered some parameter value from the literature, and we sort of we said we want to trust these values. And so basically, there is a regularization term in there too, and it's putting a relative a scale for each different parameters. And now this is our optimization. We gather all the parameters, including all this time-dependent parameters and also time-independent parameters. And for the time-dependent parameters, we discretize them in a different level of discretization. Starting from the beginning, it's cost level because we can solve the problem easier. Otherwise, starting from the like very high dimensional time discretization, the problem is easily running into some local minima. So we use sort of like a continuation for the optimization. We start from cost and discretization and go to fine discretization. And for some other data, it's not daily data of the parameters, but rather, let's say, starting from the beginning, we use monthly and later weekly. And for the daily, we use interpolation. And then we can solve this minimization problem, including 2 terms. One is a loss function, another is a regularization term with a suitable scaling parameter. This is solved by Python, the sequential linear list squares programming. And the gradient are computed by automatic differentiation using an autograd. So these are the feed for their model and data. As you can see, the data is given in red, and the model simulation is given by black dashed line. Well, it's easy to feed one type of data, for instance, number of confirmed. But however, if you want to feed all of them very well, it's really tricky. And Well, but however, here is just a deterministic fit, sort of like you optimize a problem, solve a deterministic inference problem. But if you want to make some predictions into the future, you want to equip it with some uncertainty. Oh, by the way, so this is one of the I'm sorry, one of the parameter that we're learning. The transmission reduction factor, as I said, is a time-dependent parameter. As you can see, well, towards mid-March, when the lockdown was implemented at that time, there is a significant increase of the transmission reduction. And as the lockdown was released close to the end of April, you can see clear decay of this transmission reduction. And then later on, when the number of cases got surged, people become more cautious, and this transmission reduction is getting high again. Well, as I said, to sort of like equip the uncertainty into this learning and also prediction, we put them into the Bayesian framework. So essentially, we support some prior here. We have both time-dependent parameters, and these parameters are standing for some ratio. They're in between 0 and 1, and we use some Gaussian processes to model these parameters. But there is transformation from this minus infinity to infinity to 0 to 1. There's a tangent hyperbolic function to do the transformation, and here this Gaussian process is assumed with a certain mean value, and this mean value are obtained from deterministic optimization. And then we impose the covariance. This covariance is actually one-to-one corresponding to the regularization term here. There is a H1 norm that we put here, and this is this H1 norm here for the covariance term. And now we can also get all the time independent parameters, and assume the log normal distribution for them with the mean coming from their deterministic optimization. And so now we have the new parameters, time dependent parameters, all the G collected in G, and also time independent parameters in H, and it's got the prior density as Gaussian density. And then we have the likelihood function, where we have the sort of like loss function, where we can define this likelihood function. The data is given by all these reported cases, and the observation is given by the model simulation. We have a likelihood function assumed to be Gaussian here, and these are the parameters that we learn with equipped uncertainty. Parameters, both time dependent parameters and time independent parameters, are equipped sort of like with uncertainty. And also this is their Bayesian inference with a posterior mean in blue compared to data, and also deterministic inference. You can see that at least for instance here can cover the data quite well with the credible interval, 90% of credible interval. I mean, what's the point to do this Bayesian inference, right? The point is that if you want to do some prediction to the future, for instance, if we use all the data except for the last 4 weeks, and you want to make the prediction to the future, for instance, here in the number of hospitalized cases, the deterministic prediction is going away from the data. However, the Bayesian will still give you some credible interval that it can cover the data well. Yeah, I think my time is up. Based on the Bayesian inference, you can also solve some stochastic optimization in order to slow down or control the COVID-19 spread subject to some hospital capacity, for instance. Anyway, let me come to the summary. So the takeaway message is very simple. The projected variational inference can effectively break or alleviate their cursive dimensionality as the first point. And then second, I want to say that this algorithm is scalable with respect to the number of parameters, number of samples, a number of data points that I didn't show, and also there are a number of CPU cores. But the scalability with respect to the number of data points is sort of like a weak scalability. As the number of data points grows, the number of subspace dimension for the subspace also grows proportionally. Yeah, these are the references, and also I want to mention that in a very recent work, we approximated the Wasserstein gradient direction by a neural network, 2-layer neural network with a ReLU squared activation function, and then we can transform this neural network approximation optimization problem as a convex optimization problem and solve it sort of like optimally. Thank you very much for your attention.